Hi everyone. So we did a lot of calculations based on equilibrium constant, QC, KC, and also finding the equilibrium concentration. Here's another example. What we're going to learn here is we're going to predict the reaction direction and calculate equilibrium concentrations. Okay. So the problem, the research and development unit of a chemical company studying the reaction of methane and H2S, two components of the natural gas. So CH4 and H2S giving you carbon disulfide and 4 hydrogen. So this is the balanced equation. In one experiment, 1 mole of methane, 1 mole of carbon disulfide, 2 moles of H2S and 2 moles of hydrogen mixed in a 250 milliliter vessel. Kc is given to us. In which direction will the reaction proceed to reach equilibrium? Okay. Now, since the Kc given and the initial concentrations given, we are given number of moles and volume. From this, we can find out the molarity, which is the concentration. And we put those into the Qc and then we can find out what is the Qc going to be with this given data. And then we're going to compare whether the QC larger or smaller than Kc, and then we can see in which direction reaction need to proceed to reach the equilibrium. Okay, it's easy. So we're going to first calculate the initial concentration. Methane, number of moles 1, volume 250, convert into liters, it's 2.250, 4 molar. So likewise, the number of moles of H2S over 0.25 liters, and we can find out the concentrations of all other three. Okay, so QC expression, we know how to write the QC expression, products concentrations over reactants. So when you plug these concentration values, you get 64. And the Kc was given to us as 0.036, right? So 0.036 is the Kc and QC 64. So QC is larger than Kc. What does that mean? So reactants here, products here. We have a larger QC, meaning the reaction had gone way too much to the side of the product, right? So our QC is going to be concentration of product over concentration of reactants, right? Since this number is big, in order to make it smaller number, reaction should proceed to the reactant side now, okay, from the product. So product amount need to go down and reactants need to go up in order to make the QC a smaller value. So as a result, the reaction proceed to the left. Therefore, concentration of reactants increase and those of the products decrease. So the overall reaction will proceed to make more reactants so that you can increase the reactants. By increasing the reactants, so you are increasing the denominator and lowering the products, meaning you are lowering the numerator. So the QC will come to the 0.036, which is the Kc equilibrium. Okay, so we can predict which direction a reaction should proceed. Now, in the same question, there was another part. If methane 5.56 molar at equilibrium, what are the equilibrium concentrations of the other substances? Now, let's say it reaches the equilibrium. At that equilibrium, methane concentration is 5.56. What are the equilibrium concentration of the other substances? Remember, now we are going to construct the ice table, and during the construction of ice table, we want to make sure which direction now the reaction is moving. So we started with methane, hydrogen sulfide giving carbon disulfide and hydrogen. Remember, based on the QC, we said the reaction should proceed to making more of the reactants, right? So if you write the change going from products to reactants, right? So then the carbon disulfide will react X amount, meaning it's going to lose X amount minus X. And then the hydrogen is here. That's going to be your reactants now since it's going backwards. So hydrogen Since stoichiometry ratio is 4, it would be negative 4x. And now we are making reactants more this side. Now it's going to be your products. So 2 H2S plus 2x, and this one plus x. Okay, it's a reverse, because it's reverse is what's happening. Now at the equilibrium, what's going to be there is, we know the change, it would be 8 minus x. Right, you start with 8 and then 4x amount reacted, so 8 minus 4x. This one 4 minus x. This would be now 8 plus 2x equilibrium, 4 plus x equilibrium. And we are given the equilibrium concentration of methane is 5.56, meaning 4 plus x equals 5.56. So then the x would be 5.56 minus 4, 1.56. So similarly, once you find out the x, so then the H2S is going to be 8 plus 2 times x. 2 times 1.56, 11.12 molar. Carbon disulfide would be 4 minus x, 1.56. Hydrogen would be 8 minus 4 times x, 4 times x, 1.76. So that's how you find the equilibrium concentration. Okay. Okay. Alright, so we did a lot of questions that involve equilibrium concentrations, equilibrium constant, Kc, and all that. And these are the steps in solving equilibrium problems. As a summary, solving equilibrium problems, preliminary setting up, write the balanced equation. First thing you need to do is write the balanced equation and then write the reaction quotient, okay, QC, and then convert all amounts into the correct units, molarity or ATM, and then working on the reaction table. When reaction direction is not known, then we can compare the Q with K, and then we construct a reaction table. Check the sign of the X, the change in the concentration or pressure. Okay, and then solving for X and equilibrium quantities, substitute the quantities into Q. To simplify the math, assume that X is negligible. Remember, we use the quadratic equation if not. So initial concentration of A minus X we can consider is equal to equilibrium concentration of A, or equilibrium concentration of, or initial concentration of A. And with the assumption, you solve for X, and then after you solve for the X, you can check to see if the assumption is justified, less than 5% or more than 5%. If it is not less than 5%, we do the quadratic equation to solve for X, and then find the equilibrium quantities, and then check to see that calculated values give the known equilibrium constant. Okay. Okay, so now we move on to another concept, and what is going to happen if we disturb a reaction that is already at the equilibrium. So this explained, what is going to happen explained by the Le-Chatelier's principle. So what is Le-Chatelier's principle? When a chemical system at equilibrium is disturbed, let's say you have a system and it is at the equilibrium, and you can disturb this equilibrium, okay, it reattains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. Okay, so again, Le-Chatelier's principle, when a chemical system at equilibrium is disturbed, it reattains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. We will explain this furthermore. A system is disturbed when a change in conditions forces it temporarily out of equilibrium. What does it mean by disturbing? So you do some change and then it become out of equilibrium, and then it tries to get back to the equilibrium. Okay, the system responds to a disturbance by a shift in the equilibrium position. Equilibrium position changes. A shift to the left is a net reaction from product to reactants. Remember, we saw that when the QC is greater than KC, it would make more reactants, right? So similarly, shift to the left, meaning net reaction from products goes to form more reactants. And shift to the right means a net reaction from reactants to the products. Okay. So how can we change or how can we disturb a reaction at equilibrium? One way is we can change the concentration, and let's see what's going to happen to the system if you change the concentration of reactants or products. Okay, if the concentration of A increases, okay, you can consider A as a reactant. If the concentration of A increases, what's going to happen? The system reacts to consume some of it. Let's say you have a reaction that A goes to product, right? And our QC or KC going to be products over concentration of reactant. If you increase this one, what is going to happen? Now if you increase, A is going to increase. So then what happened is, to make it back to the equilibrium, the reaction will proceed to making more of the product. So then the A will consume. Okay, so the equilibrium position shift to the right. If a reactant is added, the equilibrium position shift to the right. Now similarly, if you add a product, what's going to happen is, now this part increases, so you want to decrease it, so it decreases by going making more reactants, going from product to the reactants. So we say the equilibrium position shift to the left. Okay. And similarly, so we talk about if the concentration of A increases. And let's say you have another case. In this one, we consider B as one of the reactants. Let's say if the concentration of B goes to product, and what happens is, if the concentration of B decreases. If the concentration of B decreases, the equilibrium will go out of order. So then what happens is, to compensate the change or the decrease, the product will start reacting to get more of the B, meaning the equilibrium position shift to the left, making more of B. Okay, and then if the product is removed, let's say you are removing a product, decrease the product, so then what happens? The equilibrium position shift to the right to make more of the product. So just like the Le Chatelier's principle says, if a system is disturbed, to make the equilibrium go out of order, so then the system will adjust so that it will come back to the equilibrium. Okay, equilibrium position changes either by going left or right, but the equilibrium constant doesn't change. Okay, only substances that appear in the expression for Q can have an effect. Now what are the things that we can have in Q? Q can be concentration. If you have a concentration of like the gaseous components, and also it could be aqueous components. Remember, the solid and the liquids you cannot be in the QC. So only substances that appear in the expression for Q can have an effect. A change in concentration has no effect on the value of K. So K here is our equilibrium constant, but change in the concentration, K will not change, Kc will not change, equilibrium position will shift, but once it establish the equilibrium, it would have the same Kc. Okay. The effect of a change in concentration on a system at equilibrium. Now this one also shows what we talked about. Any of these changes causes a shift to the right. Let's say you increase the reactant. If you increase the reactant, to compensate that increase, it will go making more of the products. Same thing, Cl2 is also a reactant. So if you increase any reactants, reaction will go forward. And if you decrease any of the reactants, you are making them low. So then the reaction, the PCl5 will start acting and reacting to give you more of these ones. So the reaction will go reverse direction from right to left. Similarly, if you decrease PCl5, if you make him remove or decrease for some reason, so then the reaction will proceed making more of it. And if you increase this one, you don't want to keep it at increase, so the more of PCl5 will start reacting to give the reactants. Okay, so the green ones, any of these changes cause a shift to the right, and then the red things, increasing the product, decreasing the reactants, any of these changes causes shift to the left. Okay, predicting the effect of a change in concentration on the equilibrium position. To improve air quality and obtain a useful product, chemists often remove sulfur from coal and natural gas by treating the contaminant hydrogen sulfide with oxygen. Okay, now it is asking what happens to concentration of water if oxygen is added. Now think about which direction the reaction is going to proceed. Now what will happen to concentration of water if oxygen is added? So you are adding oxygen. You are adding a reactant. So which direction would the reaction proceed? Remember, adding any of the reactants will cause reaction shift to the product, making of the more of the products. So now water is a product. So as a result, what will happen to the water? Concentration of water will increase. Okay. So when oxygen is added, Q decreases and the reaction proceed to the right until QC equals Kc again. So water amount increases. And similarly H2S. What happened to H2S? H2S right here, if oxygen is added. What happened to H2S? Now again, when you add oxygen, you are adding one of the reactants. So what's going to happen to the equilibrium position? Is it going to go to the right side or things start moving to this side if you add oxygen? So oxygen is a reactant. Again, when you increase the reactant, so it should move, making more of the products, right? So it's asking what happened to H2S. H2S is one of the reactant. If oxygen is increases, if it goes to this direction, what's going to happen to H2S? Oxygen need to react with H2S in order to form the products. So the H2S will decrease, right, when the reaction is moving forward direction. And then the next one, what happened to oxygen concentration? If H2S is removed, you are removing this one, then what's going to happen? So what's going to happen? You are decreasing one of these. What is happening? When you decrease, more of your products will start reacting to give whatever left from here. So then reaction should move to the left side, right, making more of the reactants. So oxygen, what happened to oxygen when H2S is removed? So in that case, reaction will go left side, right? So the reaction will, if you remove H2S, you are decreasing H2S. What happened to oxygen? We are removing one of the reactants, so the reaction will proceed to the left. So as a result, since you are making more of H2S and oxygen, so oxygen will start increasing. Okay, oxygen will increase. And then H2S. What happened to H2S if sulfur is added? What happened to H2S? Okay, H2S is over here. H2S is over here. You are adding sulfur. What do you think is going to happen? Now remember, sulfur is a solid. So only thing that can affect is whichever goes into your QC. Do we put sulfur, since it's a solid, to our QC expression? No, right? So nothing will happen to H2S, so any of these reactants or the products, if sulfur is added, because it is a solid, and these quantities remain unchanged. Okay, so this is our QC and the solution also written here for you to read and understand. The same thing that we talked about. Okay, now that is what happened by changing the concentration. Now let's see what's going to happen if you change the pressure. Okay, the effect of a change in pressure or volume. So remember, the pressure and volume are interrelated, right? How are they going to relate? Remember the Boyle's law? PV is a constant, right? And then the pressure and volume has a reciprocal relationship. As the pressure increases, volume decreases. Okay, or the pressure decreases, volume increases. Changes in pressure affect equilibrium systems containing gaseous components. So this is mainly for the gases. Change in the concentration of a gaseous component causes the equilibrium to shift accordingly. Adding an inert gas. Now remember that adding an inert gas has no effect on the equilibrium position. Okay, as long as the volume does not change. If the volume doesn't change, you add any inert gas, nothing will affect the equilibrium position, because inert gases doesn't react with anything. Okay, this is because all concentrations and partial pressures remain unchanged by adding an inert gas. Change in the volume of the reaction vessel will cause equilibrium to shift. Okay, if you change the volume of the reaction vessel, that will make our reaction equilibrium to shift if the change in the number of moles not equal to 0. Going from products to reactants or reactants to products, if you have a difference in the number of moles of gases, then we will see equilibrium shift. But if the delta n, which is the change in number of moles, 0, nothing will happen. And then again, just like the concentration, changes in pressure, volume have no effect on the value of K. Since the K, here again it's a Kc, Kc doesn't change by changing the pressure or the volume. Okay, but the equilibrium position shifts and then it will become back to the same ratio. But the Kc doesn't change. Okay, effect of change in pressure on a system at equilibrium. Let's see this system, the gas phase reaction is at equilibrium. Now here we have a blue sphere and then we have a yellow sphere, and then when you mix these two together forms a green one. Okay, so let's say 1 mole of blue one plus 1 mole of yellow one gives you a 1 mole of green one. Now what is the number of moles of our reactants? 2. The number of moles of our products? 1. 1 plus 1 is 2. 2 giving 1, right? So, and this is at equilibrium, the middle one over here. Now what are we going to do? We lower the pressure. Remember, the pressure and volume has a reciprocal relationship. You lower the pressure. When you lower the pressure, what happens? Volume increases, right? So when the volume increases, what is the relationship between volume and number of moles? Remember the Avogadro law. Now as the number of moles increases, volume increases. Volume increases with the number of moles, right? They are directly proportional. As the number of moles increases, volume increases. Similarly, now we increase the volume here. Now what happened when you increase the volume? Number of moles need to increase. How can we make the number of moles increase? Is it making more of the products or going from products to reactants? If you make it a forward reaction, then you are shrinking, you are making less number of moles. But since we are increasing the volume, number of moles need to increase. How can we make number of moles increasing by shifting the equilibrium to the right or left? To the left, right? Because you can now reacting more of the products to give you 2 moles of your reactants will increase the number of moles, and because we have increased the volume. So equilibrium shift to form more molecules of gas. So it goes to reverse direction, making more of the reactants, lower pressure. Okay, even you can count the number of blue and the yellow ones. So 3 here, 3 here. Now you have 1, 2, 3, 4, 1, 2, 3, 4, right? It increases, making more of the number of moles by going from products to reactants. Now the other one, so in the other case here, you have a higher pressure. You push this piston down, making higher pressure. Higher pressure means less volume. Now less volume means, you know the Avogadro relationship. Number of moles increases as you increase the volume, and similarly as you decrease the volume, number of moles need to decrease, or decrease in the number of moles, volume should decrease. So now what happened over here? So you are increasing the pressure, lowering the volume, so the number of moles need to decrease. How can you make this number of moles decrease? By going forward or reverse. If the forward reaction, these two get together to form 1 mole of this, we are lowering the number of moles, right? So the reaction will proceed going right, going towards the right, because 2 of these combine to form 1. So since the volume decreases, number of moles decreases. You see here 3 and 3, now it has 2 and 2, and make more molecules of this. Okay, that is what happens if a reaction at equilibrium affected by pressure, volume, how it changes, which direction. Okay, even the number of moles. So you saw the 3 ways. What happened with the pressure, volume, and number of moles, which direction it should go. Okay, so we can see here, how would you change the volume of each of the following reaction to increase the yield of the products? How would you change the volume of each of the following reactions? Let's see. You have calcium carbonate giving calcium oxide and carbon dioxide. What we want to do is we want to increase carbon dioxide. What do you need to do for the volume? Now remember, calcium carbonate is a solid, calcium oxide is a solid. We have to look at what are the gases. So carbon dioxide is the only gas here. Any change will affect only if you do any change to carbon dioxide. Okay, so if you want to make more of carbon dioxide, what should we do? See the number of moles. So we want to increase the number of moles of carbon dioxide. What we need to do if you want to increase the number of moles in terms of volume? Remember the relationship, the more number of moles, the volume would be higher. If you increase the volume, number of moles will be higher. So we can increase. It is asking how would you change the volume? So we need to increase the volume. So when you increase the volume, number of moles of carbon dioxide increase, so the reaction will go proceed. Okay. So we increase the volume. In other words, what happened to the pressure? Pressure decrease. Okay. And then the next one, again we have a sulfur as a solid, 3F2, 1 SF6. So these two are gases. So we have to look at the two gases. Now look at the ratio. 3 moles of fluorine gives you 1 mole of SF6. We want to increase the yield. Yield is the products. How can we make more of this? 1. So 3 to 1 is the ratio. If you increase the volume, which direction would the reaction proceed? Remember, if you increase the volume, so then it has to create more number of moles of gases. So more number of moles are 3F2. So if you increase the volume, reaction will proceed to the left and SF6 will go down, right? But we want to is increase the yield of the product. So what do we need to do? We need to decrease the volume. So when you decrease the volume, number of moles decreases. So this is 1, this is 3. So the number of moles will decrease by going forward, right? Making more of the SF6. So what we need to do is decrease the volume for the second one, right? And in other words, decrease in the volume mean increase in the pressure. So then the equilibrium shift to the right. And then the next one, gas, 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 1 mole, so total number of moles 2, and your product also 2. So the delta N, all of these are gases, so what's the delta N? Difference in the product minus reactant, 2 minus 2, 0. If the delta N is 0, there is no change. Remember we talked about that also. Change in the volume of the reaction vessel will cause equilibrium to shift if delta N not equal 0. But in this case, delta N is 0, so there is no effect on the equilibrium position. Nothing will happen. So the change in the volume will have no effect.